Hello and welcome to the Explainer. Have you ever stopped and wondered how your air conditioner or even your fridge just makes things cold? I mean, it feels like magic, right? Well, the secret is hiding on a chart that looks, frankly, a little terrifying, but it's actually an engineer's secret map. So today, let's crack this thing wide open.
And here it is, the pressure enthalpy diagram. Yeah, I know, at first glance, it just looks like a crazy web of lines and curves, but believe me, every single line on this chart tells a story. It's the secret map that shows the entire journey a refrigerant takes to grab heat from inside your home and dump it outside. And you and I, we're going to learn how to read it.
So that's our mission for this explainer. How does this one single diagram explain something as amazing as making your food cold? We are going to decode this thing together piece by piece. And I promise, by the end, you will see your refrigerator in a whole new light.
Now, you can't read a map without a key, right? A legend to tell you what the symbols mean. To unlock our engineer's map, the very first key we need is understanding that heat isn't just one thing. Nope, it actually comes in two very different and very important forms. Okay, so first up, we've got sensible heat. This is the one you know and love. It's the heat you can feel, the kind that makes the thermometer go up. But then there's latent heat. This stuff is the secret sauce. Imagine you're boiling water. The temp rises to 100 degrees Celsius, and then it just stops. It stays at 100 degrees, even as you pour in more heat. Why? Because all that extra energy, that's latent heat, and it's being used to change the water from a liquid to a gas. This ability to soak up a ton of heat without getting any hotter, that is the absolute magic trick behind all refrigeration. So what happens if you keep that burner on after all the water is turned into steam? Well, now you're adding sensible heat again, and the temperature of that steam starts to climb way past 100 degrees. That's what we call superheating. You're just making a gas that's already a gas even hotter. And on the flip side, you've got subcooling. Think of water at 95 degrees. It's still a liquid, right? It's been cooled below its boiling point. So superheating and subcooling are really just the states on either side of that magical moment where the phase change happens. All right, so we've got our first key, the two kinds of heat. Check. Our second key is just as critical, and it's all about this really powerful relationship between pressure and when a liquid decides to boil. Here's a basic rule of the universe, really. If you put a liquid under more pressure, if you squeeze it, it gets harder for its molecules to escape and become a gas. That means you have to get it hotter to make it boil. So higher pressure means a higher boiling point. This isn't just some neat science fact. This is the control knob for the entire cooling system. And check this out. This table for a common refrigerant, R134A, just lays it out perfectly. Look at the top. At low pressure, just over 1 bar, this stuff boils at a ridiculously cold -25 Celsius. But then, crank the pressure up to over 5 bar, and suddenly it won't boil until it hits 30 degrees Celsius. Think about that. Just by changing the pressure, we can make the same liquid boil at a temperature that freezes your ice cream, or at a temperature that's warmer than a summer day. Okay, moment of truth. We have our two keys. We get that there's sensible heat and latent heat, and we know that pressure is our control knob for the boiling point. With those two ideas in our back pocket, we are finally ready to go back and decode that engineer's map. So every map needs a legend, right? Let's start with the basics. The vertical axis, the one going up and down, that's pressure. Simple. The higher you go on the chart, the higher the pressure. The horizontal axis going left to right is enthalpy. Now, that sounds complicated, but really it's just a fancy word for the total amount of heat energy packed into the refrigerant. The more you move to the right, the more energy it has. That's it. Now, you see this big dome shape that dominates the map? It divides the whole thing into 3 zones. Way over on the far left, in the subcooled region, our refrigerant is 100% liquid. Way over on the far right, in the superheated region, it's 100% gas. And inside the dome, that is where the magic happens. That's the saturated mixture region, where our refrigerant is actively boiling and it exists as a mix of liquid and vapor. That's where all that amazing latent heat gets soaked up. Okay, let's start adding some lines to our map. These are lines of constant temperature. And look at the weird path they take. On the left, in the liquid zone, they're almost perfectly vertical. But the second they hit the dome, that boiling zone, bam, they go completely flat, completely horizontal. Why? Well, remember what we just learned. When something is changing state, its temperature doesn't change. That horizontal line is the visual proof of latent heat at work. Then, once it's all gas on the other side, the lines curve down again as it gets superheated. And this is why the chart starts to look, a little crazy. We can layer on even more information. These diagonal lines you see represent other properties, like specific volume, basically how fluffy or dense the refrigerant is, and entropy. Now, don't worry, we don't have to get bogged down in the weeds here. Just know that every single line on this chart is telling us something very specific about our refrigerant's condition. And inside that super important dome region, there's one more useful measurement, the dryness fraction. Think of it like a progress bar for boiling. On the far left edge of the dome, where it's all liquid just starting to boil, the dryness, X, is 0. On the far right edge, where the very last drop has just become vapor, X equals 1. So if you're in the middle and X is 0.1, it just means 10% of your refrigerant is turned into a gas. Simple. Okay, we've decoded the symbols, we understand the regions, we've looked at the lines. Now for the payoff. This is where it all comes together. Let's use our newfound map reading skills to follow a refrigerant on a little part of its journey. So let's imagine a single drop of refrigerant. It's starting out as a liquid at a comfy 20 degrees Celsius. But then we force it through a tiny little valve, a process called throttling. Instantly, the pressure just plummets. And what did we learn? Lower pressure means a much lower boiling point. So our liquid suddenly finds itself way, way hotter than its new boiling point, and it just erupts into a violent boil, and its temperature crashes down to 0 degrees. What you're left with is this incredibly cold, misty spray of liquid and vapor. And here is the most beautiful part. That whole chaotic, violent process we just described, the pressure dropping, the explosive boiling, the temperature crash, on our map, it's just a single straight vertical line. We start at our high pressure point on the edge of the dome, and we just draw a line straight down to a lower pressure inside the dome. The map translates a complex physical event into the simplest possible geometry. That is its power. And that really gets to the heart of what this is all about. It makes you appreciate a quote like this. This isn't just a bunch of data on a page. It's a story. Every point you plot, every line you draw, is another sentence in the story of how we move energy around. It is, literally, the visual language of cooling. So let's zoom out. What have we learned today? What are the big takeaways? First, refrigeration is just about moving heat from somewhere you don't want it to somewhere you don't care about. Second, the real engine of this whole process is that amazing latent heat, which we can control by using pressure as our master knob. And finally, this elegant, beautiful chart lets us see that whole complex process, not as a bunch of equations, but as a simple, visual story. Today we only traced one little piece of the refrigeration cycle, but the full cycle, the compression, the condensation, everything, it's just a simple box you can draw on this very map. Now that you have the keys, you can explore that entire journey. You can see how it all connects. The map is in your hands now. What stories are you going to find? Thanks for watching.